And this is going to be 3.4, section 3.4, parametric motion. This is the beta lesson, okay? So this is the bottom of page 131 in your book, example 5. And it tells you a particle moves along a line so that the position when the time is 0 or greater is given by this function. Okay, where S is in meters and T is in seconds. And they have 6 questions that follow that. And so we're going to do this together. You're going to go to your calculator. You're going to go to mode. And you're going to select parametric mode. Now, we use parametric mode for one section in chapter 1 when we were doing a transformation to the unit circle. Okay, so you've been there, but you don't really think you have familiarity with it. So I go to y equals. So first thing is you're going to type example 5 in x1. What's happening? We're having the x values change position. T squared plus a negative 4t plus 3. And we're going to keep the y values constant at 1. So it's traveling along this horizontal line. And this is arbitrary where you have it traveling. You could have y equals 2, anything that fits in your window. You want to avoid having y equals 0 because you don't want it traveling along the axis because it's going to, you're not going to be able to see the path of the particle since the axes are superimposed on top of it. Okay? Next thing, go to window. This is probably the window. Now, ready? If you have an older calculator, you will definitely have less pixels. And your X-min and X-max would go from negative 4.7 to 4.7 in the Zoom 4 window. That's fine. Don't change it from what you have. Your Y-min and Y-max would go from negative 3.1 to 3.1. This one has more resolution. So you're just going to Zoom 4. And then this is the window that we had. These are the T values that were inserted. So we're starting at time 0, and we're stopping at 2 pi. That's what we did in chapter 1. We'll leave that there for now. We'll make the T step pi divided by 24. We go back to y equals. We want this to be the bouncing ball with the tail. So we go over here. We go to the left of that, push enter. Where it's set now, again, you might not get these prompts. But if I'm here, if you have a newer calculator, you can scroll through what you want this to look like. And that's what we want. We want the bouncing ball with the tail. It leaves a trail where it was. Okay? And I push graph. Now, when I push enter, I can pause the thing. Do you see what happened? The particle started at 3. See, it's always going to be on 1 because we picked that. We picked for it to travel on 1. But it started 3 to the right of the y-axis and it went left. It goes back right again. I'm in here. Well, think about this. It started at 3 because if we do the cover-up method, we put 0 in for t, then we would get a 3. It doesn't have to travel on the line y equals 1. You can travel 1.5. It doesn't really matter. Whoop. Okay. Now we're going to go down here. Now, X3 and Y3 are in there from chapter 1. They're fine. They're just out of the way. We're not bothering anything. But you're going to get down to x4. And we're going to type this in here. Ready? Vars, y vars, parametric mode, x1. And in y4, so it's going to be the same thing that's up here in x1, except instead of traveling on this line, y equals 1.5, we're going to have y4 be equal to t. So instead of the height being flat, it's going to change. And now look what happens. Push graph. Well, what happened is, sorry, the first graph's not going to type over itself unless you do something. So you can trick the calculator and tell it you changed something. And then in mode, you don't need to do this, but see this setting? Sequential mode, which means the y equals are going one at a time. You can change it to simultaneous, but it's easier to see this sequentially. But because I now typed over this, then it's going to start again with the blue graph. There's the blue graph, left, right. Here comes the purple graph. Now look what happened. The purple graph, it's rising, okay? But left and right is going the same dimensions. It starts at 3, goes left, then goes right. But because this didn't travel on a horizontal line like the actual particle did, we're left with the path of the particle. So that's helpful. I think it's helpful. The actual path of the particle is the blue graph. Okay, but that purple graph kind of tells you where it's been. Now, there are questions here. So I built this table, and here's what I need you to buy into. We are not labeling your paper A to F and answering the questions. We're building a table and then going back and saying, well, where is the answer to that? Is that in my table? So, ready? Here's my table. T is the input. S is the position. S prime is the derivative by the power rule, which would be the velocity. S double prime, derivative by the power rule of velocity, which is acceleration. So at time 0, I put a 0 in here and I get a 3. So that's the initial position. Now, if I put a 0 in here, the initial velocity would be -4. But I didn't really want to clutter this all up. I go to 2. If I put a 2 in here, the position is 2 squared is 4. Take away 2 times 4 is 8. That's a -4 plus 3 is a -1. If I put a 2 in the velocity, you get a 0. Well, that's where the particle was changing direction, when the velocity was 0. This is a 2 in the whole column. It's a constant. If I put 4 in here, it's back where it started, but it's heading right. So now I go to the question. And question A says, find the displacement of the particle during the first 2 seconds. Well, it went from -1. I'm sorry, it went from 3 to -1. It went -4. It went 4 left. Well, how did you know to make your delta table 2? I didn't know that. So, you have a rough draft of this table, and you have to move things around a little bit. B, what is the average velocity of the particle in the first 4 seconds? I want the average change, not the instantaneous change. So I do the difference of the y's, or in this case, the difference of the s's, over the difference of the t's. The numerator is 0. There was no change. Over the first 4 seconds, it was back where it started. C, find the instantaneous velocity at time 4. Well, Put 4 in the derivative, and you get 4, ready, units, meters per second. D wants the acceleration. Well, that's a constant. It's 2 meters per second, which is 2 meters per second squared. E, describe the motion of the particle. When does it change direction? Well, it goes left for 2 seconds, and then it goes right. What verifies that the particle potentially changes direction after 2 seconds? The velocity is 0. See, if I put a number less than 2 in here, you get a negative value. Put 1 in here. You get a -2. It's going left. Put a 3 in here. You get a positive value. It's going right. It changed direction at time 2 when the velocity was 0. F. We'll draw it. Well, the drawing in the textbook's on page 132. So this is what you just did. They traveled along the line y = 2. Here's what happened. It starts here, goes left, goes back right. But then they went up here and drew this in function mode. And this is really helpful because function mode complements what's in parametric mode. So the blue graph is this quadratic, the position quadratic. At time 0, you're at 3. What's happening? It's a quadratic. You got a vertex down here. So as the blue graph is falling, the particle motion's going left. And you get to the point, the input of 2. The blue graph rises, and that's when the particle goes to the right. And they've got the red graph, which is the derivative. It's the linear graph. It's the derivative of the blue graph. What do you notice? The red graph is below the x-axis from 0 to 2 when the blue graph is falling. And when the derivative is 0 at time 2, that's when this graph was changing direction at time 2. It was going from left when the blue graph is falling to right when the blue graph is rising. Okay? So this is your model, but the model being build the table. Don't go through and answer the questions chronologically. That's not going to be helpful to look at later. So we're going to pause this, give you some time to go to problem number 19, and we'll come back and go over that. All right, so we're going to go over 19. Here's our table, okay? And you should have a table like this, although you might have to rearrange it. Like this is the final draft. I don't have, my first draft of the table. I didn't know to go from 0 to 1.5. I only know that afterwards because that's when the derivative is 0. Cover-up method for the position. At time 0, the particle's at -3. I'm sorry, the particle's at 2. Sorry, the particle's at 2. Cover-up method. The velocity is negative, so it's going left. So I went over here to the calculator. You drew it in parametric mode, so I'm going to show it to you in function mode. Here's the quadratic in function mode, and here's the derivative. Okay, so what's happening? At time 0, you're at 2. The blue graph is going down, so your particle's going left. And between 1 and 2, the red graph, the derivative is 0. And the derivative is going from negative to positive. And that's when your particle's changing direction. It's only going to change direction once because this derivative is linear and it's only going to have 1 0. So that's what you're trying to get your mind around here. I don't need to redraw the graph that you have. This is. At time 0, the initial position is 2. At time 1.5, the velocity is 0. So if you put a number less than 1.5 up here, your velocity is negative. It's going left. If you put a number bigger than 1.5, so you put a 2. 2 times 2 take away 3 is positive. Particle's going right. The acceleration's constant. Here's my answer to A, B, C on the graph link, D, E, and F. So, you know, you don't go through right now and compare the answers. Yeah, do you understand conceptually what you did? Did you draw the picture? Was your graph going left and then right? It only changed direction once? Okay. Next thing, we want you to go to page 132 and just read Exploration 2 and Exploration 3 on page 133. Now, I don't want you to send this in, but understand what happened here? I took this problem, and what have you got? In this case, you have a cubic. So its derivative would be quadratic. The derivative is second degree. How many zeros does it have? It has 2 zeros. How many are real? 2 or none. So this thing is potentially changing direction twice. So this column is in function mode. Now, before we could, this is the older calculator, I made the derivative the root. So here's the quadratic, that's the derivative. And the parent graph is going up through the origin. That's that cubic. 1, 2, 3 zeros. In parametric mode, here's the picture. It's starting at 0. How do you know I'm starting at 0? Cover-up method. If you put 0 in for t, there is no constant. It starts at 0. Well, which way is it going? Well, it's going right to start with because the derivative of this would be positive. Okay? So I'm going to show you example or exploration 3, and then ask you to send in your work for 2. Okay? So for 3, you don't need to do this, just look up here. So 3 is what we talked about in the alpha lesson. They give you negative 16t squared, which is negative 1/2 times the force in gravity in feet per second squared, plus the initial velocity of 160t, plus the initial height is 0. This is leaving from the ground. And I'm having it travel on x equals 1. So I'm going to do this motion, but it's going to be vertical. Now the window, ready? If I turn this on, I need to build a window. So if I go to the table, this is telling me as high as the graph gets is 400. Yes? So I go to window, I say, all right, the y values, I'm going to have to change them. Let's go from, say, negative 40 to positive 440 so I can see this thing. I'm going to make the y scale 0 because I don't want those notches there. If I push graph, there's the particles going up, coming down, up, it disappeared. Well, it disappeared because our window, our Tmax was 2 pi. We can make this a little larger. That's the particle going up, and coming back down. That's the actual path of the particle. Not if you put it in function mode, where the input would be time. Now in the book, it's a little confusing in exploration 3 because they have you change the path. They have it traveling on 3 and then 3.1 on the way down. That's way more confusing than it needs to be. You can just travel on the same path where it came from. Okay? So that's all for 3, 4,